Most of us have a scar from the software we have built, a crash at midnight, a bug that only showed up under load, a rollback because something slipped through that we swore couldn't. This is a story about a language that quietly takes that fear off the table, not by asking you to be more careful, by making the whole class of mistakes impossible to write. Here is the uncomfortable part. Most of us ship code we don't completely trust, and we have made peace with it. We pile on tests, linters, sanitizers, review after review, an entire scaffolding built to compensate for languages that let us write unsafe programs in the first place. The bugs that hurt the most are not the careless ones, they are the ones the language allowed. And they are always the same few, a null pointer to nothing, two threads racing over one value, reaching for memory you already handed back, writing one step past the edge, smart teams, mature code bases, careful reviews, and still these exact failures ship decade after decade. At Microsoft and at Google, studies have put memory safety issues at around 70% of their serious security bugs. 70%. From code, the compiler was perfectly happy to accept. For about 30 years, the deal felt fixed. On one side, C and C++, total control, bare metal speed, and the safety problem is entirely yours. On the other, the garbage collected languages. They take the safety problem off your hands, but they charge you for it in pauses, in latency, in giving up control of memory, fast or safe. You picked your regrets at the start of the project. Rust's whole reason to exist is that this trade was never actually necessary. No garbage collector, no runtime tax, C class performance with memory safety proven before your program ever runs. And here is the shift that matters. The guarantee doesn't depend on you staying disciplined at 3 in the morning. It lives in the compiler. It's checked every time, whether you are sharp that day or not. The way it does that starts with one idea: ownership. Every value has exactly one owner. When the owner goes out of scope, the value is freed automatically at a moment the compiler already knows. Hand the value to something else, and ownership moves with it. The old name simply stops being valid. One owner, always, which means no forgetting to free, no freeing twice, no dangling behind your back, no garbage collector needed to pull it off. You don't want to hand off ownership everywhere, so instead you lend. That's borrowing. And there's one rule that does an enormous amount of work. You can have many readers or one writer, but never both at the same moment. Sit with that. If only one piece of code can write at a time and no one can read while it writes, then the classic data race is not a bug you hunt down later. It is a program that simply refuses to compile. The last piece is lifetimes. Every reference is valid for a certain span, and the compiler checks that the reference never outlives the thing it points to. That's the whole trick behind no use after free, no dangling pointers. And before you worry, most of the time you never write any of this down. The compiler infers it. Lifetimes mostly show up at the edges of your APIs, where they read less like syntax and more like documentation of what you already meant. Now, the first week with Rust, all of this feels like a fight. Everyone calls it fighting the borrow checker. But watch what's actually happening. Take this: a value freed while something still points to it. In C++, that's a use after free you find in production weeks later. In Rust, it's a message right now before you even commit. The compiler is telling you exactly what would have broken and where. That is not an obstacle. That is the most patient code reviewer you have ever worked with, and it never gets tired. The day that clicks is the day you stop fighting and start trusting it. And this is where it pays off in a way that feels almost unfair. The exact same ownership and borrowing rules that guarantee memory safety also guarantee freedom from data races. They turn out to be the same problem. The type system tracks what's safe to send between threads and what's safe to share through two little markers called send and sync. So you get to write bold, aggressive concurrent code without the usual dread, because if it would race, it doesn't compile. You might expect all this safety to cost you at runtime. It doesn't. Rust's abstractions are zero cost. Write a clean iterator chain, filter, map, sum, and it compiles down to the same tight loop you'd have written by hand. No hidden allocations, no dynamic dispatch, no closure overhead. Generics get specialized for each concrete type instead of boxed. You write for clarity and you get the performance for free. You genuinely don't have to choose. Two of the most quietly radical features do their work in the type system. There is no null. Absence is a type, option, either some value or none, so you can't accidentally reach into nothing. And there are no exceptions flying up through your code. Fallibility is a type 2 result right there in the signature. And match is exhaustive, which means the moment you add a new case, the compiler makes you handle it everywhere. The gap you would have shipped gets caught, not deployed. None of this would matter if the day to day were painful. It isn't. Rust ships with cargo, one tool for everything: build, run, test, format, lint, generate docs, publish. There is no per project build system archaeology, no arguing about formatting because there's one obvious way to do each of these. Add a dependency from crates.io and it's versioned, locked, and reproducible. Open a Rust repo you have never seen and you are building it in minutes. Boring in the best possible sense. Add it all up, and the real return isn't any single feature, it's confidence. Because your invariants live in the types and the borrow checker, the compiler behaves like a regression suite that's always running. Refactors that would terrify you in a dynamic language become almost mechanical. Change the type, follow the errors it lights up, done. Fewer production surprises because the surprising cases got caught at compile time. And your system's thinking sharpens because modeling ownership quietly forces you to design cleaner boundaries. So, in the end, Rust is more than a language, it's a discipline. It asks you to be explicit about ownership, about sharing, about failure, and in exchange, it removes a whole category of fear from building and changing software. You are not just writing code, you are writing responsibility into the thing itself, so it holds up long after you have moved on. Performance without fear. Once you've felt it, it's very hard to go back. If you enjoyed this video, drop a like and subscribe. And tell me in the comments what you want me to explain next.